Hey, in this video I'm going to show you how to get an extremely precise fit by offsetting the surface of an STL mesh. So what do I mean by offsetting the surface? Making the part thinner or thicker, and we can do that selectively in different parts to get a precise fit. So I thought a good example of something that you'd really want to fit would be this orthodontic aligner. So it might hurt your teeth if it were too tight. It might rattle around if it were too loose. So we're going to use this as a cool example where you'd really want a precise fit, or it could be quite uncomfortable. Okay, so to start off, I'm going to import my liner here, and I'm going to use the kind of default zero offset import. I'm going to make that blue just so that we have this as a reference. And the first thing I'm going to show you is super simple. We're going to use the offset body here in nTop to subtract 50 microns, just 50 microns from the surface. So everywhere it's going to get thinner by 50 microns, and let's look at the difference. You can see the blue one is just a little bit thicker than the gray, which is our minus 50 micron offset. So that, might be a way to just, let's say you had some, slight tolerance issues in the print process. You could adjust for that by my realist tiny adjustment. Maybe just to make it super obvious, even more obvious of what we're doing here, I'm just going to drag in what happens if we offset this entire thing by 1 millimeter. And you can see these calculations are not instant, but pretty fast. So this would kind of be like a goofy, you probably would not want this in your mouth, but just to show you, okay, that is clearly a lot different than the original one. So this will just give you maybe a more explicit visual of what offsetting means. Okay, so let's do something maybe more complicated. What if we wanted to test two different offsets to see kind of what the right fit was? So we could, for example, A/B test two different offsets. So on one side, I centered this plane kind of right in between the two central incisors, and on one side of this plane where it's negative, I'm going to actually have no offset, and on the other side, and again I'll make this kind of on the bigger side, I'm going to show you we're going to have a 250 micron offset. And so let's just really quickly look at what the field for that would look like. Again, nTop's all about field driven design. So again, on the left side of this plane, right, it's going to have no offset. On the right side, it's going to be 1/4 millimeter. And then we'll turn off field view and see what that looks like. So here you can see through to the blue, there's no change on this side. We've got a pretty big change on the other side. So that could be a really cool way to test slightly different offsets to do a fit test. And again, we're doing this with an aligner for teeth because better be comfortable. But you could think about this for all kinds of things, connecting two parts together to get a nice snap fit or press fit, etc. Okay, so finally, I just want to show you the real power of using field-driven design to offset this to get a super precise fit that's very nonlinear, right? So what I'm going to do is I've put this pink sphere on one of the canines, and the sort of test example cases we're going to say this, when this person put on this liner, this tooth just felt too tight. It was hurting right around there. So we picked the problem tooth. We kind of located the sphere. Again, it doesn't have to be a sphere. I'm just using this as a simple example. So now let's go look at the field of this guy, and we're gonna have to bring it up here. Here we go. So look, so the field of my new ramp here is if I'm more than 7 millimeters away from my sphere, give me 0. So let's probe. So there's no offset everywhere here. And then if I'm inside or at the surface, it's going to be, I picked 70 microns. Here, let's bring this sphere back so we can see this. So right in the middle there, we're going to have a 70 micron offset, and then inwards to make more room, because it's our test case of it hurting, and then that's going to ramp away and fall off right until we get to 0. So what would the part look like in that case? So we're applying that offset field to very, very precisely, oops, let me turn off this one, here we go, to very, very precisely tune in on this. And let's just compare this to our blue. So you can see here that the gray one, it's kind of hard to see, but is shrinking ever so slightly in that canine pocket because, or the mesh is thinning, more accurately, inward, but only in that tooth. And everywhere else, if you look, it's very hard to see any change at all. Actually, this is a good view. Look, watch. Look at the canine. It's kind of moving. None of the other ones are moving. Let's just go really in there. See? So everything else is staying the same between the control, and that canine is getting thinner. So that is an example of how to offset an STL in nTop in 3 different ways. One uniformly, one with this kind of idea of an A/B test, and finally a really precise fit. Say, oh, just this one tooth is off, I want to fix that one. And now I guess the final step to actually being able to use this again is going to be we're going to have to make a mesh again, make an STL again, to take it out of nTop. I have a very fast tool that I've created here that's going to create a mesh via voxel grid. Nothing mind-blowing if you're familiar with nTop, but a quick utility that makes workflows with these very complex geometries very fast to output both accurate and reasonable file size meshes. So if you want, we'll include a link below to give away my special meshing compound block, and hope you enjoyed this. Please subscribe to the channel, and would love for you to ask any questions about what is going on here in the comments below. Thank you.